everyone, and welcome. Thank you all so much for joining us today for this live stream event. My name is Alexia, and I am the project and event manager of the Microsoft Reactor Toronto. I will be sharing session resources with you in the chat. But before we begin, I'd like to quickly review two items, our code of conduct and event guidelines. First, please take a moment to review our code of conduct. Microsoft Reactor seeks to provide a respectful environment for both our audience and presenters. We do encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. And secondly, our event guidelines. This session is being recorded and will be available on our Microsoft Reactor YouTube channel in about 24 to 48 hours. I will be sharing the link to our YouTube channel in the chat. But if you've not been on a live stream through YouTube before, please note that you must create an account on YouTube in order to access and interact in the chat. You can set that up now, and if you're unable to use the chat but have questions, feel free to reach out to us on social media or on Meetup. Which brings us to today's session. I'm going to bring in our speakers here. Hi, Josh and Josh. How are we doing today?
Great.
Fantastic. Well, thank you so much for joining us today. We're super excited to have you for this session. Yeah, thank you, and take it away.
Awesome. Well, good morning. My name is Josh O, and I'm working as a PM intern with Project Bonsai at Microsoft. Would you like to introduce yourself, Josh?
Thank you, Josh. My name is Josh N. I'm a cloud developer advocate at Microsoft for the data team.
All right, and today we'll be discussing how Project Bonsai can assist with the development of autonomous AI systems. All right, so for today's session, we'll start with an introduction to autonomous systems and AI technologies, followed up with an overview of the Project Bonsai platform and service. The latter section of today's talk will then focus on a specific application of Project Bonsai, Project Moab, and then we'll go more into depth on how Project Moab uses Bonsai with a live demo. So before we jump in, let's take a look at an example of how Project Bonsai has been used successfully in the industry.
What makes the perfect Cheeto? Precision. The right ingredients, the right size, shape, flavor, air, coming together to make the perfect crunch. It's really important that our Cheetos are in specification each time. We've partnered with Microsoft and Neil Analytics to deliver the perfect product to our consumers. Our engineers know how to make a Cheeto. They understand the day-to-day, what the machine looks like, the vibration, the pressure. They take all their knowledge and train the AI. Then they assess how the AI is making decisions through millions of simulations. After we've trained it on all these different parameters, it's continually tracking the performance coming off our extruders. It flags real time if there are issues so we can intervene very fast. And what's great about the autonomous systems is that it upskills our workers. It's actually the perfect combination of human and machine. Our trial runs have all been successful. Now we're starting to scale. Innovation is such a core value for PepsiCo, and Cheetos is so integral to that. We wanted to make our consumers happy with every experience. And autonomous systems are going to help us raise it to the next level. We're just getting started. We're ready to rock and roll.
Look how useful having an adaptive system was for PepsiCo. As we continue to talk about Project Bonsai, you'll get a feel for how useful autonomous AI can be for various applications. But first, let's backtrack and focus on a thought experiment. I want to ask you the question, how would you teach someone to balance a ball on a plate? The way I think about it is by answering or identifying the question and asking myself, how would I do this? Suppose I place a ball on a paper plate. Whenever the ball travels away from equilibrium, i.e. the middle, I make an action. I tilt the plate to correct the position, and after each action, I assess the situation, the state, and proceed. Through an iterative process, trial and error, I would eventually be able to learn how to balance the ball pretty well. Unfortunately, I would probably still drop the ball because I haven't yet thought about adjusting for the velocity accrued from being at an angle. As seen. And as we can see here, there are already several constraints that are used to teach myself how to complete this task. If I were teaching someone else this task, it would be beneficial to break down the complexity of balancing a ball into its components, like I just did. And now, if I were designing a system to complete this task, I would teach it the same way that we teach humans, through a paradigm called machine teaching. And we'll talk about that in a bit. But before we investigate the components that make up AI systems, apologies. So before we talk about AI systems a little bit more, I'd like to go back even more and talk about the history of optimization and control systems. So AI systems have ushered in the next evolution of industrial systems. However, control and optimization systems weren't always smart. In the first industrial revolution, we harnessed steam and electricity to power mechanized systems. Nearly a century later, we began automating industrial systems with software. For example, we use PID controllers and PICs, which stand for proportional integral derivative and peripheral interface controllers, respectively, to automate systems using feedback loops. And these systems operate on a rigid fixed set of instructions. And these are great for systems that had expected operations that would happen over and over and over again. But any time that there was a process that varied from the expected operation, these systems are unable to adapt. This is where autonomous systems shine. Powered by AI, we can infuse the physical world with intelligence and create systems that can learn. Now, while autonomous AI can be a powerful tool in the modern age, there are some specific attributes that show us whether an intelligent implementation is beneficial. For example, having highly dynamic systems with lots of variables can make it hard for traditional automated systems to operate optimally. With multiple variables, competing optimization strategies may also cause traditional control system issues. Due to the complexity of some of these systems, operators may also not be privy to the starting conditions for an operation. And additionally, operators may also be overwhelmed by how complex their systems are. And all of these contributing factors can majorly affect the overall performance of a said control system. Now, with the implementation of autonomous AI, having something like a Bonsai brain or an autonomous AI can allow for the adaptation and learning to happen and occur within the system. And this covers a lot of blind spots of traditional automation. Now let's take a look at some more industrial applications for Bonsai. Parts of the Redmond, Washington Microsoft campus actually have Bonsai controlled HVAC systems. This helps Microsoft not only save money, but also produce great working environments for its employees. Bonsai brains are also used in the manufacturing industry to optimize machining. This means increased throughput or improved precision for CNC operations, which stands for computer numerical control. In this case, these CNC machines often make precise additive or subtractive changes for manufacturing processes for materials. And for a company like NOV, the Bonsai model takes an average of 13 seconds to actually calibrate compared to an expert operator, which has a benchmark of 2 hours. And that's an invaluable amount of time saved. As we already introduced with the PepsiCo example, Bonsai can also be used to manage supply chain operations. And additionally, Bonsai also has been used to manage the operations of chemical processes. With an intelligent system, processes like keeping a specific temperature and pressure for a pressure tank at a chemical mixing plant can be done with more certainty from the operators. And each of these examples paints a similar story where autonomous AI helped optimize a complex system. So we've talked a lot about what Bonsai can do, but not as much about what it actually is. So what is a Bonsai brain? We've heard about it in the Pepsi video, and now we've talked a little bit about AI models. The Bonsai brain is actually a high-level AI model. We use it to generate optimization and control actions for complex industrial systems. And how do we do that? We build it by combining techniques in deep reinforced learning, and we'll talk about that in just a moment. We also use simulations. We're using simulations to teach an AI like a human. Our simulation serves as a learning environment, basically a classroom. And we want the most authentic and accurate training environment for our brain. Finally, we use a paradigm called machine teaching, which we'll also discuss briefly. So we've talked about reinforcement learning as part of the Bonsai brain. Well, now let's talk a little bit about reinforcement learning and the fact that it's really unlike other types of machine learning models. You start out first with supervised learning, where the data is labeled and you pretty much know everything you need to know. You can do things like classify whether something is an A or a B, or do a forecast or prediction, like how much or how many. Then you move into unsupervised learning, where the data isn't labeled, it's not organized, but you can still use that for things like anomaly detection. Is this a dog? Is this a cat? Is this weird? How is this organized? How is this clustered? But the thing is, neither of those can approach and answer the question of what should be done next? What should I do next? And that's where reinforcement learning comes in. So now we've talked a little bit about reinforcement learning, which answers the question of what should be done next? What should I do next? And now we're going to talk about deep reinforcement learning. Let's break that apart. We learn by practicing, as we said before, in a simulated environment. And as we see here, we have this little robot, and that's our agent. You can kind of think of this example in a similar way. If you've ever played chess, you're the agent. Your environment, in this case, is our simulation or your chessboard. The state is the positions of all of you and your opponent's pieces. If you're playing Super Mario, you jump over something. If you're in a chemical reactor, you're looking at the temperature inside or the concentration. If you're trying to balance a ball, you're looking at where the ball is. What is its X and Y positions? What's its X and Y velocities? Those sort of things. You're going to take an action. You're going to move your queen, bishop, or pawn, modify the reactor temperature. You're going to change the plate angle and the ball's location and velocity. And if we do that correctly, we assess and then we get a reward. So deep reinforcement learning is a process that optimizes a system to find the quickest path to a reward possible. One pass through this is called an iteration. And then we have something one level higher called an episode, and that lets us set how long we want to iterate or stay within our learning loop. Now, there's also the word deep in deep learning. Deep learning is typically used in things like object recognition systems. And you've probably been a deep learning system yourself. If you've ever done something like CAPTCHA, where you're required to pick out the boats or crosswalks or something similar out of a picture, you're doing the exact same thing with your eyes, your sensors, as they sift through all of that information to find exactly what you need. And when you put those two things together, deep learning and reinforcement learning, you have deep reinforcement learning, and that allows us to take a system that's optimized to find the quickest path to the reward and scale it out using techniques to find exactly what you need. And that's the basis of pretty much every complicated and sophisticated AI system out there. So now you have a foundation for deep reinforcement learning. Machine teaching takes this one step further. Now with the sport baseball, most people wouldn't think to teach a 5-year-old how to hit a baseball by pitching a million fastballs at them or showing them videos of major league pitchers. And yet this is how we approach machine learning today. We show machines large amounts of data and expect them to learn associations, find patterns on their own. For many of the most common applications of AI technology, such as simple text or image recognition, this approach is fine. However, for programming systems in complex and dynamic environments, this standard approach to machine learning is unrealistically time intensive, and often it can be ineffective. If I were using machine learning, I would cluster all the great players by their position. Who's the best pitcher? Who's the best catcher based on statistics? Now, this can be a great way for simple operations, but I wouldn't be able to go through and learn exactly like a human does. I wouldn't be able to learn the game because I wouldn't know the rules, I wouldn't know the objectives, I wouldn't know the goals, and I really wouldn't be able to answer the big question, what should I do next? And so machine teaching sits on top of reinforcement learning, where reinforcement learning would be the coach. You run to the coach and you say, hey, coach, I want to play the sport. And then the coach turns around and says, okay, great. After 8, 9, 10,000 games, you're going to start Saturday and you'll be great since I believe in experience. That's machine teaching or machine learning. Now, machine teaching takes that one step further. Anybody who really knows the game, pitchers, catchers, or whoever's on the field, they say, hey, that's great. I know how to do this. I have subject matter expertise, and I have a curriculum with learning path, goals, objectives to get you any skill that you need to learn. We start with one skill, one concept, then we go on to the next one, and the next one, and so on and so forth. And that allows us to scale our expertise. And then because we're doing it this way, we can build on this. We can achieve faster training times, and we can have some explainability and share those concepts better. Now let's take a look at why the combination of machine teaching and reinforcement learning can be so powerful. So we've talked about what a brain is, and we've talked about the importance of reinforcement learning and how it's different from the other approaches, because it answers that question of what should I do next. Now, using Project Bonsai It allows us to take these AI models, these brains, and build them, train them, and then deploy them to a device. So we take our machine teaching, we take our subject matter expertise, and we use them together. We do that through a single purpose language called Inkling that we'll see when Josh N does his demo in a bit. But that allows us to define everything we need to teach concepts, goals, and objectives to our brain. Also, it defines what simulator we're using. We integrate our simulator in the service as our most authentic training environment. It is containerized, so we have several instances that we can use to scale out our brain training. Now, what makes this possible is the AI engine, and it looks at that Inkling and it determines what's the appropriate algorithm to use. It creates the neural networks that we need, it tunes all the hyperparameters, and everything that an AI expert would do, it does it for us. Then it orchestrates the training, and it monitors that training, gives us feedback so that we know when our brain is done training and when we're satisfied with the level of proficiency. And then once we're done, we can just deploy and scale that into the real world. So we're getting ready to see this demo. We've got some prereqs that we need before any project. We need to make sure that we integrate our classroom, our simulator, before we even get started. We also need to create an AI specification to understand our system and make sure that we can decompose the problem and understand all of the information needed so that we can write that Inkling code. And then we need to set up our brain training, our brain definition document, and then we can go through that process of training and assessing until we're ready, and then deploy that brain on the device. And that's what you're going to see right now. So it can be hard to demonstrate the Project Bonsai platform because most systems are pretty large and complex. That's why we created the Project Moab hardware kit to illustrate the end-to-end toolchain of Project Bonsai. As we just observed through the Project Bonsai workflow, we can take a deeper look at the training, assessment, and deployment process through Project Moab. And we can observe how the state and action of our system plays into the learning process throughout the demo. All right, it's time to switch. Take it away, Josh.
Right. Thank you, Josh. Thank you for covering all the details towards the introduction to Project Bonsai and helping us understand more about machine teaching and deep reinforcement learning, as well as the Bonsai platform. Now, I'll go ahead and show a demo of the Bonsai platform, and using the same scenario that Josh talked about, the ball on a plate system, where we are going to try and model a system that can be able to balance a ball on top of a plate. Now, to do this, we're going to start off at the Azure portal. So go to portal.azure.com. And then from the Azure portal, we're going to create our Bonsai workspace. And then using this Bonsai workspace, we'll navigate back to the web UI portal so that we can be able to teach our brain. So once you are on the Azure portal, once you're on the other Azure portal, I'm just going to click on create a resource. And then right inside here, we're going to search for Bonsai. And then just going to select that one, create. And then from here, you can just complete this wizard with all the necessary information, then review and create. And these will go ahead and provision your Bonsai workspace. I had already created a Bonsai workspace before. And so I'm just going to switch over to the Bonsai web UI portal. So to do this, you can just go to the preview.bons.ai, and this will launch Bonsai web UI portal. And from here, you can be able to follow along. Once this launches, this takes some time to load. Anyway, once that launches, you'll be able to see the web UI portal that looks like this. If you don't already have any brain, it's just going to be empty, and then we can be able to create a brain together. So to create a brain, I'm going to click on create a brain, and then I can be able to select from a list of the different brains that we have. For this example, I'll be using the Moab brain. So I'm just going to click on Moab, and then you can provide a name for your brain. So this is, I'm going to give it a name, Moab 260722A. And then click on create brain. This will go ahead and create a new Bonsai brain for you. Now, Once that creates the Bonsai brain, it now opens the full teaching interface that we're going to use for teaching our Bonsai brain. The teaching interface has three main parts. One, we have this left pane right here that shows you a list of all your brains, simulators, dataset, and also exported brains. Now, if it's the first time you've created your Bonsai brain, then you'll just see the Moab brain that you've created right here. But you can be able to see I had another Moab brain that I had created before. There was this Moab brain that I had created before, and also there's this new one that I've created now. Another good thing is you can be able to see a list of all the versions of the Bonsai brains that you've trained. So in this case, you can be able to see it has a V01 right here. But if I go ahead and train and also realize and make changes in the future, make changes to the Inkling code right here, then I can be able to have a different version of the Bonsai brain inside here. So this the Bonsai platform provides you also with an inbuilt versioning system where you can be able to track different versions of your Bonsai brains. Another thing that is listed is the simulators right inside here. So if it's the first time you've created the Moab brain, you'll be able to see it also created a Moab simulator right inside here. The Moab brain comes by default it has this default simulator that is created the moment you create your Moab brain. But alternatively, you can be able to add your own simulator from a link of all these different simulator partners like AnyLogic, MathWorks, or alternatively, you can be able to build your own simulator using Python or even with C#, and you can be able to link it directly from here. So if you've built your simulator in MATLAB, you can be able to link that directly here, and you can be able to use that particular simulator to train your Bonsai brain. The other part is the exported brains. So the moment you train your Bonsai brain right inside here, you can be able to see all the different, you can be able to export, and you can be able to see the different exported brains right inside here, as we'll see as I proceed. And the most important thing to notice is that, as I mentioned, we have different versions of your Bonsai brain right inside here. So that means you can be able to export the different versions that you've trained for your Bonsai brain. So suppose I train a new version of the Bonsai brain, and then I realize it doesn't perform as I wanted it to perform, and I have a previous version that was actually working. I can be able to export the previous version and be able to deploy it as well to my device. So that's the left panel. So I'm going to minimize this. The next part that we have right inside here is the coding panel. So this one right here is where you are able to define your brain using Inkling. So Inkling, as Josh had mentioned, is a single purpose language that we use to train our Bonsai brain. So right inside here, this is where you can be able to this is where you define your brain using Inkling. And the last part is the graphing panel, which shows a graphical representation of your Bonsai brain. So right inside here, you can be able to see a graphical representation of everything that we've been able to define using Inkling right here in the middle. Now, before I proceed and explain more about Inkling, I'm going to turn on or toggle this little button right here called Visual Editor, just to show you something else. Once I toggle the Visual Editor, it replaces the coding panel with a graphical representation of the Bonsai brain. What this allows you to do is to be able to just drag and drop the different components onto this canvas and be able to define your Bonsai brain. Let's have a look at the different components of the visual editor, of the visual authoring. Now, the first component of the visual authoring is the concept picker right here. So the a concept in Bonsai represents a component of the brain that must be learned, selected, programmed, or imported. So, and this concept picker will allow us to pick the different components right here. There are 4 different kinds of components that we support on Bonsai. The first one is a learned concept. We also have a selector concept that allows you to select or choose more than one concept. We also have a programmed concept, and you can think this as a function a function just like you define when you're writing code. And the last one is an imported concept that allows you to import a fully defined machine learning model. The other element of the visual authoring The other component of the visual authoring is the brain diagram. So this is a graphical representation of your bonsai brain. It includes the state, the concept, and even the simulator, as we'll see in more details in the Inkling code. And the last part of the visual authoring, the last component of visual authoring is the properties editor. So this is used to display and edit the global properties. So what that means is if I navigate to one of the components here on the brain diagram, I can be able to see and even edit directly from here. So I'm going to toggle this back so that I can go back to the Inkling code and we can have a look at the Inkling code for the Moab. So once I toggle back to the Inkling code, we can walk through the Inkling code and try and have a deeper understanding of this. So to begin with, right here on the graphical representation of the bonsai brain, we have the state, the observable state that is defined right here. So as Josh mentioned, when we're trying to balance a ball on the plate, there are two particular properties that you'll be looking for. One, you'll be constantly monitoring the position of the ball. That is the X and Y coordinates of the ball the X and Y coordinates of the ball on the plate at any given time. And the other thing that we'll be monitoring is the velocity of the ball the velocity at which the ball is moving across the plate. And then using these two, you can be able to adjust the pitch and the roll of the plate. Now, that's the first thing that we are able to define, the states. So these are the states that we receive from the simulator after each iteration. And so we'll be monitoring the X and Y position of the ball. That's the first state. And also the other thing we'll be looking at is the velocity of the ball. Now, this state, I'll then this state is then fed into the concept as an input. So we have an input, the states being an input to the concept. As mentioned before, the concept is a component of the bonsai brain that must be learned, imported, programmed, or selected. So the concept contains two important things. We have the curriculum right here, and then we have the goals. Let us start with the curriculum. Now, the curriculum will define how the training engine should train the bonsai brain. So this is where you define how the training engine actually trains the bonsai brain. You can see we also specify our simulator right here that we'll be using for training the bonsai brain. Then let's have a look at the goals. The goals and objectives, which are also part of the concept. So the objective of training, for this bonsai brain is expressed as a goal with two sub-goals. So for this one, we have two sub-goals. The first one is do not let the ball fall off the plate, and the other one is to drive the ball to the center of the plate. Now, these two goals, and you can see we've been able to define them here, the avoid and the drive. I'm going to switch to a different tab right here so that I can be able to explain in more details about the goals. So we have four different goals in Project Bonsai. The first one is the avoid. So the goal of the avoid objective is to teach the AI how to prevent the environment from entering a particular state. Think of this as preventing the ball from reaching to the 80% reaching to this 80% area or rather constraining the ball within the 80% area of the plate to avoid it from getting to the edge of the plate and falling off. So in the case of Moab, the avoid objective is used to prevent the ball from reaching the edge of the plate and falling off. And you can be able to see the associated Inkling code right here. The other goal that we support in Project Bonsai is the drive objective. So the drive objective basically gets the target as quickly as possible. Gets the environment state to the specified target as quickly as possible, and also ensures that it remains in the specified target. So for this case, we are trying to drive the ball. In the case of Moab, we are trying to bring the ball to the center of the plate and ensuring that it remains at that. So we ensure that the plate balances the ball at the center of the plate. So if the ball is near the edge or is away from the center of the plate, we try moving it as close as possible and we maintain it at the center of the plate. Therefore, for this case, you can be able to see the associated inkling code right here for the drive objective. And you realize these are the most important objectives. These are the most important objectives that we'll be trying to meet in the Project Moab, for Project Moab. But we also have other objectives that we support on Project Bonsai, and the other one is the maximize objective. So the maximize objective will push the target as quickly as possible beyond the desired threshold. So what that means is you will increase the average test value as much as possible within the target range. However, you need to specify an upper bound for the target range. So in the case of Moab, we don't leverage the maximize objective, but if we had upgraded our device with a temperature sensor and a heater like a mini HVAC, then the maximize objective will be to maintain a specific state for a very high temperature. The other objective is the minimize objective. So the minimize actually teaches the AI that it should decrease, or rather push the target value as low as possible below a desired threshold. So for this, you include an upper bound, and then you try to push the target value as low as possible below the desired threshold. You realize this is just like the direct opposite of what the maximize objective is actually doing. Then the last objective that we are also leverage for the Moab, the last objective that we also support for Project Bonsai is the reach objective. So the reach objective, this one teaches the AI to get to a desired state as quickly as possible, but unlike the drive objective, it is not required to keep the system in that state. So it works the same as the drive objective. However, for the reach, it's not a must. We do not need to maintain the system in that particular state. So these are the major, these are the main goal objectives that we support in Project Bonsai. And so coming back to the inkling code, you can be able to see the two goals that we're using here to teach the AI. So we have the avoid. So we start with the keyword, the goal itself, avoid, and then the name of the objective is fall off the plate. So, and then we specify it right here, and then we have the drive objective, and also we specify it right here. Then from the concept right here, I want you to notice when we're defining the concept here, we have the input as the state, which we defined, which was the position and which was the position and velocity. And then you notice the output of this concept is the simulator action. So we have the input, which is the observable state, and the action will be the action the simulator takes is the output from the simulator. So if you come and see, the simulator action will includes only two things. One will be adjusting the pitch and the roll of the plate. So the pitch is the rotation about the x-axis, and the roll is the rotation about the y-axis. So once the AI lands, depending on the curriculum that you've specified here, and also the goals that you've specified here, once it lands and once it's taught right there, it takes this specific action to adjust the pitch and the roll of the plate. And so the action right here is served as an input to the simulator. So let's have a look at the simulator. So the simulator, as Josh had talked when explaining about deep reinforcement learning, or rather the reinforcement learning loop, we use simulators in Bonsai to provide a safe environment to train the Bonsai brain. Think of this: if in the event you are training an intelligent agent to perform actions in the real world, there will be some downsides to that. One, because you're doing that in the real world, there's a limitations to how many iterations you can be able to perform. And also, when you're trying to train a brain that works in a dull or dirty environment, then there is the case or scenario of safety. However, when you're doing this in simulation, it makes everything easier because there's the possibility to do very many iterations, and there is less concern or less worry about safety. So the action that we do here is now fed into the simulator. And remember, we already specified our particular simulator or our specific simulator package right here in the simulator section. So inside here, we have our simulator that takes in the action, the action from the concept as an input, and then it applies that. And then from that, once it applies the particular action, in this case, adjusting the pitch and the roll of the plate, we then have new states. So like, because the ball moves, once you adjust the pitch and the roll, we'll have a new position of the ball, and we'll also have a new velocity, and that becomes the output from the simulator. And so we have a new state, and then once we have a new state, the new state is then comes in as an input to the concept. We have an output as an action, and then an input. The action is an input to the simulator, and we have a new state. And so this builds, or this creates the reinforcement learning loop that Josh had already talked about in the past. When he was going through the slides. And so through these different iterations, we are able to teach the intelligent agent on how to balance the ball correctly at the center of the plate. Now, you may be wondering what happens in the real world when you finish training, and then you deploy. Right here, this is where you can have like your actual real device, and then the AI is able, because it has learned, it's able to apply the actions to the particular device that you've been able to deploy. Now, once you've been able to define your Bonsai brain using Inkling right here in the coding panel, next, you just click on the train button, and then this automatically switches to the train tab. And from here, you can be able to train your Bonsai brain. So I'm going to switch over to a brain that I had already trained, since this might take quite some time to start the simulators and also train the Bonsai brain. So I have this one here that I had already trained. So I'm going to switch to this one that I had already trained, and you can see that the training was already complete. All right. Just before I start explaining this, let's switch to this one that we've clicked on. Train. And just so that I can just highlight some few things when the brain is starting to train. The first thing you noticed was it was trying to connect to the simulator that we've already specified here. So in this case, if I connected to my own simulator, maybe running on MATLAB, I could it will actually just connect to that particular simulator. The other thing you notice, it starts some assessments, and one more important thing, you can be able to see this simulator visualizer that shows you that has an indication of the training of the Bonsai brain. Now, the other thing is the training performance chart is loaded right here, and I'm going to switch to an already trained brain so that I can be able to explain more about the training performance chart. All right. Okay, so let's switch to the training performance chart. Let's switch to the brain that we've already trained. Okay, so right here you can be able to see this is the training performance chart, and inside here you can be able to see the goal satisfaction plot. So you can be able to see this graph that has several plots. So we have the goal satisfaction plot, that is this one right here. We also have the two objectives. We have the avoid falling off the plate. The goals that we had already defined, the goal objectives we had. So there is this one right here, which is the avoid falling off the plate, and we have the other one right here, which is the drive to the center of the plate. Now, the other thing that I would like to highlight are the assessments right here. So as And I'm going to switch just a little bit to this one as well. As the bonsai brain is training, yeah, this one has already started. You can be able to see it starts running automatic assessments right here. So this hasn't yet loaded. I'm just going to stick and use this one, the one that we've already trained. You can be able to see the different assessments that the bonsai brain is running at a given time. So, sorry, as it's training. So these assessments are run regularly during training, and these automatic assessments, they evaluate the brain performance with they evaluate the brain perform they evaluate the brain performance without the exploratory actions used during training. So you can be able, if I click on any of the assessments right here, sorry about that, I'm going to have to zoom out a little bit so that it can be visible. So if I click on any of the automatic assessment iteration right here, you can be able to see the overall success rate, success rate from here, and also you can be able to see the brain performance. So as you move down these different iterations, these different assessments, you can be able to see how the brain has been performing across during the entire training process. Now, once the brain has completed training, in the like this one, the next thing that you need to do is click on export the brain. So once you click on export the brain, this exports it in a Docker container, and you can be able to select the architecture. So for the Moab, because it's running on a Raspberry Pi, I'm going to select the ARM32, and then you can be able to change the name, but I'm just going to keep it as it is, and then click on export. So once you click on export, you can be able to see the progress of the Bonsai platform exporting the Bonsai brain. So right here, it's going to take some few minutes. All right, okay. This is taking a little bit longer. Just a few more minutes.
Hey Josh, could you unmute yourself?
Oh, sorry about that. Thank you, Josh.
No
All right,
worries.
so this is taking a little bit longer to export the Bonsai brain. So, however, once it completes exporting, you can be able to see the deployment instructions right here, and you can be able to use Azure IoT Azure IoT Edge to deploy your Bonsai brain as an Edge module. So you can be able to use this and deploy the Bonsai brain onto your IoT Edge device. And once you deploy, you can be able to see the performance of the Bonsai brain on the real device. So I'm going to show you a clip of this. So after deployment, this is how the Bonsai brain actually performs. So you can be able to balance, it's able to balance the ball at the center of the plate using the brain that we've been able to train. Josh, back to you.
Awesome. Great. So thank you, Josh, for talking a little bit about Project Moab and kind of demonstrating the workflow that's related to just going through Project Bonsai and talking about that training workflow, creating that inkling, talking about the simulators and everything that goes into training, going through the learning loop, and eventually deploying and exporting your brain to your device. Right. So as we get back into our presentation, I just want to again talk about the Project Bonsai workflow. Alexia, do you think you could switch back to the slides? Awesome. Right. So, we already talked about this, but, Josh kind of went through an actual live demo using this exact workflow applied to Project Bonsai. So just a brief overview and just to revisit this diagram, we went over our specs, we prepared our simulation, we looked at the Inkling code, and we trained our brain using our simulator. We also deployed our brain, watching it perform in that video. And all of this is an iterative process. And we talked a lot about iteration and about episodes. But what I mean by iterative process is if we change something in our Moab, let's say tomorrow we release a new Moab that has new abilities, and there's like the plate's bigger or some other variable is different. We can actually take our previous simulation, change the Inkling a little bit depending on what new inputs there are, and then go all the way through this process again. We can go through the prereqs again, we can go through the cloud, train a new brain, a version 2, as Josh mentioned while he was going through Project Moab, and then we can redeploy that brain to the new device and test its operations. And that iterative process allows us to create new brains more easily and more effectively for our systems. And now that you have an improved understanding of the Bonsai workflow, you can start to think about designing your own brains. All right, so if you'd like to look at some more examples of how autonomous systems tackle problems, you can actually use this interactive demo here. So with the link provided, you should be able to get a feel for how an autonomous AI works and what it's capable of. And you can kind of try to be an AI yourself for these different scenarios. Personally, I am very, very bad AI when it comes to managing these different systems. So you should definitely try it out, and you'll get a feel for how hard it is sometimes to manage these systems. And before we finish, there are some additional industry applications featuring Project Bonsai, and I'd like to talk about a couple of those. Some of these you may already recognize from earlier in this talk. There are others like Bell Aerospace and SCG that may be new to you, but each of these companies utilizes Project Bonsai in a different, unique way that solves their own complex control problems. One cool application for Project Bonsai that we haven't talked about yet would be for Bell Aerospace. Now, Microsoft Project Bonsai actually uses a brain in Bell's drones, and it basically just gives Bell an edge in reacting to the physical environment during flights. So if you'd like to learn more about any of these examples, much more in depth, you can actually use the link provided to go take a look at each of these examples and learn more about them. Awesome. That about wraps up our talk for today. Appreciate everybody listening, and please feel free to reach out to any of us if you have any questions about the content, any content discussed or shown today. If you want to learn more, there are actually a few links on the screen right now. There's also going to be some links shared in chat by our moderator. Have a great rest of your day. Thank you.
Hey, I'm just jumping here. Thank you both so much for today's session. It was great to have you. Thank you again. If you have a few more minutes, feel free to provide your feedback on the link that I shared right here. The event code is on the screen as well as in the comments. And yeah, if you're interested in joining more of our sessions, we're on YouTube. Obviously, we have this session that's been recorded as well as all of our other sessions. We're also on Meetup. You can join our community on meet up, sign up for future events. You can also join our community on Twitter. And yeah, again, thank you both so much. I'll be sharing more of the links that you provided in the chat for resources. And on to the next one. Thank you all so much.
No problem. Thank you.
Bye.